So now we're going to take today in this class a bit of a review break here to help us get ready for the test you're going to get. I'm going to go first over the homework that you were assigned last class, which was group work 13. So I'm going to go to that right now. So let me share the screen here. And here we are. And I crossed off a bunch of problems on there we didn't need to do. So let's go through some of these. I'm sure you have this down, but I just want to make totally sure. We've got 6 different problems we'll do quickly here. I've crossed off the other 2 so I have more room. You realize that for a rational number between 35.62005 and 62006, if you add the 2 together and divide by 2, you would get this. Am I finished? I am, because that is a terminating decimal, which means it's rational, so that problem is all finished. All right, I really don't have to do anything else. Okay, if I go to the next one, all right, if I add those 2 together on my calculator and divide by 2, I would get 4.00621535, and that's a rational number also, so I'm all finished with that one. So I could make other rational numbers there if I wanted to, but why bother, right? I ask you to come up with a rational number that's between them, and you have. All right, and last but not least, the last one. Okay, if I add the 2 together and divide by 2, I would get this. And guess what? I'm all done there too. Don't have to do anything else. It's a rational number. I'm completely finished. All right, so now let's go to the irrational number situation. Let's do the first one over here first. Again, when you add these 2 numbers together and divide by 2, you get this. Well, for this particular one, I'm going to be lazy. And I'm just going to stick some numbers on here. 1, 6, 2, 8, 5, 3, 1, 9, 4, 7, ... If I saw this answer on your paper, I would realize that you had come up with an irrational number. It's all over the place. Let's go to the next one. Okay, for this one, I'm going to divide by 2 again, right? Add the 2 and divide by 2. Sorry, my numbers are wavering up and down. For this one, I'm going to put a couple numbers on there, 2, 8, 6, 5, 3, and I'm going to be lazy and simply draw an arrow. The Kellyism arrow says what? This number goes on forever to infinity. It never stops, and it's all over the place. So that's done. All right. So let's go to the third one number. Okay, I'm going to start way over here. 315.20305255. I'm just going to pick out any pattern I want, any numbers I want. How about 1, 2? So let's do 1, 2, 1, 2, 2, 1 followed by 3 2s, 1 followed by 4 2s, 1 followed by 5 2s, and 3 dots. ... That is definitely an irrational number showing a growing pattern, and it is between the 2 given numbers. I didn't leave you much room to do those, did I? So I figured I'd better do that. All right? So those 6 questions are finished, and you'll have 1 of each on the big test you're going to take very soon. Okay, now there are no other questions that I left uncrossed off here because they are not on the COVID Big Quiz 2. Okay, so I've blown up the other problems to a little bigger size here, and there's nothing here I really want you to do for this quiz, and we can skip this one also. But I would like to just quickly zip through these two problems just to make sure you're comfortable. This, remember, is 739, 739, 739. It is 0, 6, 18, or 8, 0, 0, 0, 0, 3x, and 0. I think I've got a good chance at being able to add across here without screwing it up like the last class I did. But at any rate, 3x plus, it looks like it's 7, has to equal 0 mod 10. All right. What does 3x have to end in so that when it's added to 7, okay, it gives me what I need, 0 mod 10. Well, let's see. What number times 3 ends in a 3? Wouldn't it just be 1, right? So let's try that out, okay? So if it's a 1, if x is equal to 1, I get 3, I add 7 to it, I get 10, right? Oh, you know what? I made a mistake. I can see it already. You know why I could see my mistake? Because I know this bank routing number. It used to be a very big bank in the Buffalo area. This isn't 1 over here, okay? So let me erase this quickly and erase my error, okay? Get all this out of here. This shouldn't have been 1. This should have been an 8. So this is 18, which is 8. And when I add these numbers together going across, it looks like it's 14, right? Okay, so it's 3x plus 14 has to equal 0 mod 10. All right? And so my number has to end in a what? It has to end in a 6 in order to end up with what I want, right? So I want 0 mod 10. So what does x have to be? X has to be 2. All right? So this number down here should have been a 2. That routing number, 022 followed by 4 zeros and 20 is HSBC Bank. And HSBC Bank moved out of Buffalo. They said, you guys in these branches aren't doing us any good. We're going to go with the big money, okay? Guess what? They're coming back. They're beginning to open bank branches around the Buffalo area again. They've been gone probably 15 years. But, hey, you know, they learned from their mistake, perhaps, maybe. I don't know. All right, enough editorializing. Let's go to the UPC code. 3131, 31, 31, 31, 31. Keep an eye on me, make sure I don't make a mistake. 2, there's 18, which is 8. 7, 0, 0, 0, 0, 6, 2. So this is Weber's horseradish mustard. What is their UPC code that is on the bottle of mustard? Well, let's see. If I add across the left to right, I have 7 and 2 is 9, and 8 are 17, and 7 is 24, and another 8 would be 32. Let me see if I can add and get the same thing going the other way. Okay, let's see. So that's 8 with 7 is 15. 15 and 8 is 23, 24, 25, and 7 is 32. So what does 3x have to end in? It has to end in a what? An 8. So what number times 3 ends in an 8? Well, 3 times 2 is 6, 3 times 4 is 12, 3 times 6 is 18. Look at that. X has to be 6. All right? So since x is 6, 3 times 6 is 18. 32 added with 18 gives me 50. It checks out. So x has to be 6. Here x had to be 2. I will give you one of each of these on the quiz coming up. Hopefully you know how to do them just real well, and that'll give you some points. All right, there are 2 more here. All right, I'm thinking I might have the answers here. Let me see if I do. I think I do. So those 2 answers should be it was those 2, I believe, right there. So you should have gotten x equals 8. I think this one up here is the credit card, yes. So you should have gotten x equals 8 and x equals 7. Okay, so there you are. So you know those are going to be on the test. Hopefully those will help you get a good grade. Excuse the cold coffee sip. All right, so we have completed everything I wanted you to try on 13. But I thought, what the heck? We'll take a couple minutes and let's go back. I have another sheet I had put together over here that I was supposed to use to help me check your homework when you came to class. So I thought I'd go through these real quick with you again, like we did the other day. So here we go. All right, which computation of those 4 there is correct? Is 8 to the 3rd power 6 mod 10? Well, what is 8 to the 3rd power? Well, if you can't remember, let's turn on the calculator and find out. 8 caret 3 is 512. 512 mod 10 should be equal to what? Should be equal to 2 mod 10. So that's no good. A's no good. Let's look at B. What's 5 times 12? 60. What's 60 plus 30? 90. 90 ends in a 0. Same thing as 0 mod 10. Looks like B's okay, right? Is C all right? Or what's wrong with it? Well, it's 39 when I multiply it out. I divide it by 5. 7 times 5 is 35 with a remainder of 4. This says 3, no good. On a mod 10 clock, 11 hours past 5 is what time? Is it 0? 11 hours past 5 would be 16 o'clock. In mod 10, that would be 6. That's no good either. So it was choice B. You will be asked some questions about clock arithmetic on this test, so be ready to realize that that's going to happen. The next 3 consecutive Luca numbers after 843. What is the next number? Excuse me. What is the number prior to 843? Here are 3 consecutive Lucas listed. How would I get that? It's the one before it. Well, wouldn't it plus 843 have to give us 1364? So if I take 843 away from it, 1, 2, and 5, it should be 521, right? Okay, let's go on. 3, if a single layer of paper is folded 14 times, how many individually stacked sheets of copy paper should have the same or equal height? All I need to do is do what? A power of 2, exponential growth. 2 caret 14, 16,384, which is choice D. Which number that follows is not rational? A is definitely rational. It's got a fraction. B is definitely rational because it's got a terminating decimal on it. And D terminates, but you know pi doesn't terminate and it doesn't repeat. It goes on forever. So your correct answer is pi. Choice C. Which number that follows is a rational number? Okay, well, I didn't use bar notation to help us out here, did I? So looking at those, I think you can see that A has a growing pattern. 316, then it's 3166, then it's 3 1 and 3 6s. So the sixes are increasing. It is definitely an irrational number. But notice, in B, 38, 38, 38, 38, 38, 38, 38, 38, 38 forever. That's a rational number. And of course, phi, you know, is irrational. So the correct answer is B. Which number that follows is irrational? Well, it's not A because it's 26, 26, 26, 26 forever. That's a repeating decimal, no good. It isn't B because 2581 finally begins to repeat later in the number, so it would go on to infinity because of the bar notation. And of course, my crazy arrow that's on there tells you what? This number goes on forever. This decimal, it's all over the place. Therefore, it is irrational. What type or types of numbers is 94? Well, it certainly isn't imaginary. It certainly is real, right? Okay. Is it irrational? No, I don't think so. Is it whole and irrational? No, if it isn't irrational, it can't be whole and irrational. So guess what? It's all of these. It's rational, it's an integer, it's a whole number, it's a natural number, and it's a real number. Which number types identify the number below? Well, it appears to have, going on to infinity, to have a growing pattern in it, right? 315, then 3155, 3135s. All right, so therefore it can't be rational. It's definitely real. So it's got to be choice C, right? It is irrational and real. Which of the numbers below here is rational? Well, it doesn't appear to be that first one because it's got a growing pattern, goes to infinity. All right, can't be that one. How about B? Gee, it's negative, but that's okay. It's got a bar notation in it, drinking notation, 0.65, 65, 65 forever to infinity. C, D, and E all have arrows after them, and to me, what do arrows mean that you're supposed to understand? They go on forever. They are all over the place. They are not rational. They are irrational. So the correct choice is B. What's the exact value of the golden ratio? Once again, I keep hitting you with that. It is 1 plus square root of 5 all over 2. State the golden ratio as a decimal rounded to 6 decimal places. Phi is 1.618034. You know that already. Viewing the two numbers behind the arrows, which statement is true about the number that's called M? Now, the first thing you got to decide is M between them? And what kind of number is M? Well, if you look at M, it has a growing pattern on it. The ones are increasing, right? So it's definitely an irrational number. Now, is it between those? 6.431? The fourth decimal place is definitely not between the two. So this is an irrational number that is not between the numbers shown behind the arrows, right? So it should have been choice D. Look at 13. Viewing the numbers behind the arrows, what's true about this number? Does it have a growing pattern on it again? Definitely has the 3 dots, goes to infinity, so it certainly isn't rational. It's got to be irrational. Is it between them? I believe you can see that it is, because this would be 1, 0, this would be 2, 0, And here we have 5, right? 1, 5. So it definitely would be between them. So this is a what? An irrational number that is between the numbers behind the arrows, which is choice B. I give you these questions just to make you think a little bit. Viewing these two numbers behind the arrows below, which statement is true about the number called y? Notice it starts out with a 6, 9 after the decimal point, but then it's 2, 5, 2, 5, 2, 5, 2, 5, 2, 5 forever. That means it's what? Rational. Now, is it between them? Well, it looks like it is, right? Looks like it is. 2, 5 is between 20 and 30, so I think we're okay. So this is what? A rational number that is between the arrow numbers, okay? On 16, you were supposed to have done the back, correct? Do you think you have problems like 7 and 8 down now? Let's just walk through what the process is. You take the two numbers, add them together, and divide by 2. Once you get that answer, okay, you know that's rational. So you've got your rational number already. When you go to the second part of the question here, you have to turn it into an irrational number, either by putting an arrow on it, putting a bunch of numbers on it that are all over the place, showing that it goes on forever, but make sure you put the 3 dots, or you can simply put an arrow after your answer, which is a Kellyism, which tells me that you know that number would have to go on forever, okay? So I don't think we need to go over those. We just reviewed them very well, okay? Now let's just take a minute to look at these. How do you convert those fractions into their decimal equivalents? You take the top, you put it in your calculator first, and you divide it by the bottom. All right? Look at 12, please. Okay? In problem 12, statement E, or question E, would be what? 5 and 72 over 99. There are 2 repeating numbers there. F would be 2, right? And there are 3 numbers repeating there, so you put 036, or you can just put the 36 if you want, over 999. And for G, you would use -2, and I'm going to leave this arrow off. I would put the 495 over what? 4 9s. Are you required on the test to reduce those? No, you are not. Okay? Now, let's go over and see if I have the answer key to this sheet, and I believe I do. So here are some examples that work for the first 2 up at the top there. All right, you know that we said we didn't have to do anything with the first one. The second one, I don't know if my picture's blocking it or not, but make sure you have 3 dots on the end if you decide to use 1, 2, 1, 2, 2, 1, 2, 2, 2, 2, and all that. All right, and here are the answers down towards the bottom. I reduced these, but you don't have to do that, all right? But we had the numbers right, 495 over 4 9s, 36 over 36 should be over 3 9s. That should not be a 0 there. That should be 3 9s. Okay, and I believe it does reduce correctly to 2/55, but I honestly don't know. I can't believe it does. Okay, it should be 36. Oh, excuse me. Excuse me. I'm incorrect. You can't use the Kelly's cheater method to do this, and this is probably wrong. So, I'm sorry. So, no, we can't do that. Now, I don't remember if the problem I gave you that I sent home with you or not, if it had a 0 without the bar over it. I assumed I put the bar over it, If I didn't, you can't use the Kelly's Cheater method to do it. Okay? Don't worry. The one on the test, you can use the Kelly's Cheater method. All right, 13. I got that x would have to be 8. 8 times 7 is 56. It added to 34, all right, gives us the answer 8. All right, we have very quickly and hopefully to your satisfaction reviewed both sheets that I assigned, which were group work 13 and parts of group work 16. Should have a shared screen up here now, and away we go. All right, the natural numbers. We've talked about them extensively over since even the beginning of the course. And if you recall, the natural numbers are the numbers that you learn to count with, okay? If we write them using set notation, if you recall, it would look something like this. You would write 1, 2, 3, 4, 5, 6, 7, and we use the ... notation for people to realize that it goes on to infinity. And of course, without the braces, it's called a list, but with the braces, it's called set notation. So you are very much familiar with the natural numbers. Then we discussed the fact that when you got to school, you learned that there was another number you needed to be able to add, subtract, and multiply these whole numbers. And well, that made the set of whole numbers actually, and that number was 0. So when you add 0 to the set of counting numbers, you have the set which is referred to as the whole numbers, okay? And of course, we discussed this at length a couple of weeks ago. Then you looked outside the kitchen window and you realized that there were numbers below 0 on the temperature scale that you saw out there. So therefore, you realized that there was another set of numbers with those minus signs in front of them. And of course, they're not called minus numbers. The numbers, when you put the whole numbers that have minus signs in front of them together with these numbers, you have what is called the set of integers. Now, we are used to, as a kid, writing the set of integers this way. You would come in from negative infinity, go out towards positive infinity, and use the ... notation. Well, and you know that I have suggested to you that we don't have to write the numbers this way. We actually can write these numbers using only one direction to infinity. So in other words, we could rewrite this set a little differently by writing it as 0, 1, -1, 2, -2, 3, -3, 4, -4, ... And notice now we are heading to infinity only in one direction. You know that all the numbers that are integers would be there if we continued this process the way we've started it, using the same pattern, 5, -5, 6, -6, and so forth. So both of these are decent and acceptable representations of the set of integers. Now, before you learned about the integers, you learned about those awful things called fractions. And fractions, of course, are defined in our number system by a different name. And as you recall, the name given to the fractions are, or is, the rational numbers. Now, I'm going to write out the definition again for the rational numbers. You already probably know what it is, but just in case you can't remember, I will write it out nice and slowly now here for you. A rational number is any number that can be expressed as the quotient of two integers in the form A over B, where B cannot be equal to 0. Now, you will recall, we have discussed this prior to what you're seeing now. You cannot divide by 0 in our number system. You know that. When you do it on a calculator, you get an undefined answer or an error. So division by 0 is totally impossible. That's why rational numbers cannot have zeros as denominators. Now, as you recall, with rational numbers, the Greeks felt that all numbers could be expressed as the quotient of two integers. And as we have discussed, they found out they were wrong because you cannot write all numbers as the quotient of two integers that we can possibly think of. I'll come back to that in a moment. But if you recall, the rational numbers have two ways that they behave if you try to divide them out and convert them into decimals, okay? So let's take a look at that. Let's take the fraction 4 over 3, or we can make it 4 over negative 3. If you divide this out on your calculator, you find that you get 1.333333, and the 3's just keep on going forever. Of course, it should be a negative sign here. That is one thing that can happen when you try to convert a rational number or fraction into its decimal equivalent. That's called repetition. And if you recall, repetition can be shown the way I have it up there now, with the 3's and the 3 dots after them, or it can be expressed using what I call drinking notation or bar notation. And you recall this from middle school: when you put the bar over the 3, it means the 3's continue to repeat forever. So there is one example of one type of outcome you can have when you convert a rational number into its decimal equivalent. The other type of number you can get when you convert a rational number into its decimal equivalent, if you recall, is a decimal number that terminates. It stops, okay? So for example, if I use 2/5, let's say I use the fraction 4 2/5, that will give me a 4. If you divide 5 into 2, you will get 0.4, and it doesn't go anywhere else. It's just 0.4. If you divide 5 into 2, all right, it goes exactly 0.4 times, okay? So this decimal has what? It has terminated. So how I usually have you show that on a test is, if I ask you on the test, which you know I'm going to, what is the decimal behavior that occurs when you take a rational number and convert it to a decimal? One of two things can happen. It is either going to repeat, so you can put down a capital R, or it is going to terminate, a capital T. I will accept those as answers, okay? So I have no problem with you showing me a capital R or a capital T. Now, we have begun to discuss how you change these decimals back into the fractions they came from. The only one I'm really concerned with you remembering for this test that's coming up is the following. I want you to be able to remember that when you have a repeating decimal, all right, I've got on the wrong page here, excuse me a minute. Let me erase all this. Okay, give me a second to do that. Okay, when you take a repeating decimal, as long as it's a chunk that you are trying to change back to the fraction it came from, for example, what if I use 7, excuse me, I better turn on the writing utility here. If I want to write 7.315 bar as the fraction it came from, remember you would keep the 7 because there are 3 digits repeating in the 315. you can use what I call the Kelly's cheater method to convert that back to the fraction it came from. So it would simply be 315 over 3 nines. Okay? Now, I'm not requiring you to reduce that fraction, but if you take a calculator and you take the calculator and take 315 and divide it by 999, you will get on your calculator 0.315, 315, 315, 315 forever. Okay? So we're going to also talk about ways to change these fractions back into, these repeating decimals back into the fractions that they have come from. Okay? So that is part of the material you're going to have to know for the upcoming test. Now, we then discussed that the rational numbers, which by the way can be whole, rational numbers can be integers, rational numbers can be natural numbers, all right? But they don't make up all the possible numbers we could have in our number system. And if you recall, we found another name for a given set of numbers which are not rational. And the first example we came up with was pi. If you take a look at pi, which of course is 3.1415927 to about 7 decimal places, pi does not repeat as a decimal. If it did repeat as a decimal, we could turn pi into a fraction, okay? And so therefore it would be rational because it would be the quotient of two integers. Pi does not have that characteristic. Neither does phi. Phi, of course, we have been discussing it in class also, 1.618034. It continues on forever, all over the place, okay? It's not a repeating number at all. And since it goes on forever like this, just like pi does, it is referred to as an irrational number. Remember, irrational numbers mean not rational. Ir means not. Rational is a quotient of two integers, but an irrational number is one that doesn't have that characteristic, okay? Your typical radicals that you're used to seeing, radical 2, radical 3, radical 11, the ones that, quote, don't come out even, are also examples of irrational numbers, okay? All right. Now, hopefully you have remembered this from the discussions we have been having in class, but I did want to briefly go over it with you just to make sure you're aware of it, because this information will be tested on this test you're going to take called Virus Quiz number 2. Okay, now, when you put together the irrational numbers and the rational numbers, remember the rational numbers can include the whole numbers, the integers, the natural numbers, okay? When you put all these numbers together, you have the set which is called the real numbers. So we're not going to deal with imaginary numbers at all in this class. So we're going to say that the largest set of numbers, it's obviously infinite, that we are going to deal with is the real numbers. They are made up of rationals and they are made up of irrationals. Now, hopefully, this short review has been helpful for you to be able to help you continue with what we're going to discuss today for reviewing for the Virus Quiz number 2, which you're going to take over the weekend. I would just like to go back here for a moment and take a look at this term right here, ... notation. You recall that if we want to show something is continuing in the same pattern, we can use this ... notation. For example, if I want to show that I have a decimal that is repeating 4 5s, I can put 3 dots after it to show that that continues in the same pattern, okay? All right, that pattern is what we call repetition, and we can use it for 0.45 bar here. All right? Now, 4. There are other numbers that you can have that show patterns, but the patterns are not repetition. The patterns actually have an irrational behavior to them. Let me give you an example of that. I can have 0.45, 455, 4 followed by 3 5s, 4 followed by 4 5s, and if I put 3 dots after that, what that means to the reader is that this number continues to infinity, but the number of 5s continues to increase using the same pattern. First there was 1, then there were 2, then there were 3, then there were 4. So next there will be 5, then there will be 6, and so forth. This type of number right here, I'm going to call it the number A. A is irrational. It is irrational behavior for a number to show that kind of a growing pattern. The number above it is a rational number. I'm going to call it B. B is rational. The reason B is rational is I could convert that back to a fraction which it came from. Irrational numbers cannot be converted back to fractions because they didn't come from fractions. Therefore, they have irrational behavior. So I want you to get used to the idea that rational behavior shows repetition that's exactly identical in each step, whereas irrational behavior, if the number shows a growing pattern, then the number shows irrational behavior. Greetings once again. We are about to do a very weird problem. So I thought I'd bring it right up right now and have a look at it. The sheet is called Group Work 16PF. Group Work 16PF. So make sure you have that available. If you'd like, you'd even can print it, but I don't think you need to print it. You want to work on it with your pen tablet and send it back to me because I'll give you the 10 points for it. So let's bring it up here and take a look. All right. It says, here's a crazy problem we're going to try. Assume you have 5 composite numbers, all of which have prime factorizations which consist of a single prime number, not the same for the 5 composite ones we're going to deal with, and 4 other primes which are identical to each other, but different for each composite number. Here's an example of a number that is formed in the way we're discussing. All right? The prime factorization, for example, of 891 is 3 times 3 times 3 times 3. See, there are 4 3s there, and an 11. Okay? Now, the 5 composite numbers listed below are configured in the same way. Okay? Now, you are to determine the prime factorization of each composite number, see which prime in each prime factorization is the unique single prime number in each one of the prime factorizations. And once you have done that, you are to take those 5 unique prime numbers you found and determine what composite number the 5 unique primes form when multiplied together. Now, once you get that number, here's what you have to do. Once you've determined that new composite number, you are to convert it to a mod 18 number. So I want to know that number that you get, all right, when you multiply those 5 unique primes together, okay, I want to know what the value of that number is in mod 18. Okay, well, let's get to work on this thing. All right, let's get to work. All right, so here are our 5 numbers. Okay, so let me get my pen tablet going here, and away we'll go figuring these out. Well, looks like 496 shouldn't be too bad. We need to get its prime factorization. I'm going to go over here, and we're going to write down 496, not too low, but low enough. Now I can tell that's an even number. So I think what we better do is divide it by 2. And get your calculator handy so that you can do all this work. I'm going to get mine over here also. Okay, so I'm going to take 496, I'm going to divide it by 2, and when I do, I get 248. So write that down on your paper, 248. Well, that's still even, right? So we can divide it by 2 also. So it looks like the numbers that are going to be the same in this prime factorization, 4 numbers that are going to be the same are going to be 2's, right? So if I take 248 and I divide it by 2, I obtain 124. So let's get that down there. Let's divide it by 2. And that is what? 60, I believe, 2. And if I divide that by 2, I get 31. So 31 is that unique prime number I'm looking for in that prime factorization of 496. Okay? So I'm going to write over here, 496 is equal to 2 to the what? 4th power times 31. So 31's that one crazy number we're looking for in the first composite number. Well, let's shoot over to 8125. Let's go over here with 8125. Let's see what we can do with that. Well, you recall your divisibility rules. 8125 ends in a 5, right? So it should be divisible by 5. So on your calculator, take 8125, like I'm doing, and divide it by 5. When I did, I got 1625. Well, it appears that 5 is going to be my repeating number in this number's prime factorization, because this is also divisible by 5, right? 1625 is. So I'm going to divide that by 5. And when I did, I get 325. And I'm going to hit that by 5 also. I'm going to hit divided by 5 equals, and I get 65. And you know that's divisible by 5 as well. So we should get the different prime now in this series of numbers. And of course, it's going to be what? It's going to be 13. So the prime factorization for 8125, all right, is 5 to the 4th times what? Times 13. So the number we are looking for this particular prime factorization is 13. All right, so we've got 2 of the 5 finished. Let's keep trucking along. So let's go to 1377 and see what we can do with it. Well, it's not divisible by 2. It's certainly not, excuse me, divisible by 5. I wonder if it's divisible by 3. Let's check it out and see. Well, let's see. 7 and 7 is 14. 14 and 3 is 17. And 17 and 1 is 18, right? So it appears that 1377 is divisible by 3. So let's try it out. So again, on my calculator, 1377 divided by 3 is 459. Well, I'm hoping I can divide by 3 again, but I don't know yet until I add the digits together. Well, 4 and 5 is 9, and 9 and 9 is 18, so it appears this is divisible by 3 again. That's a break for us, right? Now, so that means our four same prime numbers in here are all going to be 3s, it looks like. So I obtain 153. Well, I would assume I'm going to be able to divide that by 3 also. And you can see if I add 1, 5, excuse me, and 3 together, I get 9. So that's divisible by 3. So is 153, right? So I divide this and I get, it looks like 51. Oh, is 51 divisible by 3? It sure is. And you get what? 17. So the crazy number we're looking for here is 17, right? So writing this prime factorization down for 1377, it appears I have 3 to the 4th power times 17. My magical number is the 17. Now, it looks like these are getting a little harder, right? So let's see how 7203 fits us, or how we can do with that. All right, so I'm going to write down 7203 here. Now, unfortunately, 7203 is not divisible. Oh, wait a minute. Maybe it is divisible by 3. If I add 7 and 2 together, that's 9. And 9 and 3 is what? 12. Well, gosh, looks like we caught a break there. So this is divisible by 3. At least we'll get it to be smaller. 7203 divided by 3 equals 2401. Now, unfortunately, we know this is not going to be more 3s, is it? And the reason we know it's not going to be more 3s is because we have 4 3s in this one. Remember, we said that the 4 identical numbers in the prime factorizations were not going to be the same in the 5 different numbers. So we're all done with 3. Plus, you can see 3 doesn't divide into 2401. Well, we got to start testing, right? So let's see. 5 won't go in. How about 7? Well, let's see. Let's try it dividing by 7. Oh, it worked. So 7 was the next prime, and it actually worked. So hopefully, the numbers we're going to be looking for here are going to be all 7s. I assume they've got to be if the directions are correct on the problem, right? So let's try 7 again. So divided by 7 equals 49. That's an easy one, right? And we know that's divisible by 7. Okay, so our original number, or the number we're looking for, that's the single digit in the prime factorization, in this case is a 3. And we can write the prime factorization of 7203 as what? 7 to the 4th power times 3. Well, we got one more to do, and that's 29,282. I'm going to put it over here, 29,282. And now I'm going to attempt to divide it by what? Well, looks like it's even, right? So let's divide her by 2. Let me get it on my calculator here. 29,282. Whoop, I didn't get it in there right. Let me try again. 29,282 divided by 2 is, all right, 14,641. Well, it appears that I'm not going to be able to use 7 to divide into this because I had, if you look at my pen over here, I had all 7s here. I had all 5s up here. I had all 3s over here. Okay, what did I have on the other one up there? All 2s, right? 4 2s. So it appears that it's going to have to be 11 or something larger. Well, let's hope it's 11, all right? So let's see how it works out. So if I take that number, 14,000, 641, and I divide it by 11. Well, we're hoping it comes out even. It does. Oh, what a tough break. All right, so that is divisible by 11. I get 1331. Well, I think there's a pretty good chance 1331 is divisible by 11 from what the directions of the problem said. So let's hit that, divided by 11. When I do, I get 121. And of course, I think you remember that 121 is 11 times 11. So our prime factorization here for 29,282 is 11 to the 4th power times what? Times 2. So let's see. The single digit we're looking for here is the 2. So the prime factorization of the number I'm going to try to convert appears it's going to be what? It's going to be 2 times 3. All right, now what else have I got up here that I've circled? Okay. Come on here. 2 times 3 times what? 13. So it looks like 13, 17, and 31. 13, 17, and 31. So that's the prime factorization of the number that I'm supposed to convert. All right, so what is that number? Well, let's multiply them out and see. 31 times 17 times 13 times, well, we can just do 6. 2 times 3 is 6. I got the answer 41,106. So my question that I have to answer for this problem is simply this. 41,106. That is correct. Now I need to convert that number, okay, into what? A mod 18 number. So my question is 41,106, let me make a bigger 0 there, is equal to what number mod 18? Well, I have to divide that by 18, right? I have to divide it by 18, so let's do her. So if I take 41,106 and I divide it by 18, what do I get? So I get divided by 18, because that's my mod number, and I get 2283, and I get 0.6 bar, it looks like, on the end. Well, of course, I throw that away. So I take 2283, and I multiply that times what? 18, because I need the remainder, right? And I got 41,094. So when I subtract these two numbers, the difference I get is what? It is 12, right? So 41,106 is exactly identical to 12 mod, that should be a D there, mod 18. Now that was a little bit crazy, wasn't it? But what we did is we refreshed our memory a little bit on prime numbers and prime factorization. And we, of course, realized that to do the conversion, you must get the whole number that 18 goes into how many times with 41,106, take the 2283 and multiply it by 18, and we got our remainder, which is what we needed, which was 12. Okay, now you do have a video quiz to do for me tonight, okay? and to get you ready for our next class. And that video quiz is called, let me see if I can find it here, VQ 13BB. I put two B's behind it. So we're going to work for homework, video quiz 13BB. And this will also help you review and think about the stuff that's going to be on the test coming up in a few days. Now, please listen to this carefully. Your only homework assignment is going to be to do the video quiz and send it to me. All right? We will open our next class on Thursday, if you are in a normal session for either spring or fall, with Group Work Virus 1, and we will go over that. And we will do Group Work Virus number 2, and those are designed to get you ready for the test coming up, which you will get over the weekend. Okay? So, with no further ado, I wish you well on video quiz 13BB, and I want you to do a great job on that, and get ready because we're going to do some tough reviews work in your next class. So until then, take care.